Hello, everyone. Welcome to the Python tutorial session on optimizing the trading parameters for the Pulse trading strategy using Bayesian optimization. So let's get started. So first, we install the Blowtorch, which is a package to allow us to do Bayesian optimization as a global optimization technique for the trading parameters. And again, we need the Y-Finance package to download the data. All right, so here again, we have this list of packages to import, and we will mention additional packages along the way, right? So we also control the seed so that it's reproducible in terms of the results. Okay, so first, we talk about the black box function class. So talk about in the lecture videos on Bayesian optimization. Basically, it is a technique for us to locate, search for the global optimum of a black box function. So here in this case, I'm treating the Pulse trading strategy as a black box function that accepts the inputs and produce the outputs, right? So the input, in this case, I'm designing it to be the entry threshold and exit threshold, right? So these are the two tuning knobs that I can play around with. And the final output is the activity here, which is the Sharpe ratio, right? To analyze return over analyzed volatility, right? So this is Sharpe ratio. In other words, I want to find the parameters for entry and the exit threshold such that the Sharpe ratio is maximized, right? It's maximum. That's the problem I'm faced with. So here, this class, the purpose of this class is that we wrap the whole calculation of Sharpe ratio in a single class, right, in a single function, so that it's easier to treat it as a black box. So here we have a class, and I'm subclassing the neural network module. Note that this is optional, right? You can choose not to subclass any parent class, but in this case, I'm choosing to use it because it's easier for me to just call the function later on because of the call function. So it's just a small utility function here. And the initialization function, I pass in the figure pair, which is the pair of stock symbols that I will use to analyze and start dates and dates of the stock price. And then the risk-free rate to calculate the Sharpe ratio, right? So I store all this in my attributes along with the stock. So stock means that I have this function to download the data of interest, right? So I have the stock pair and then start and date. So this is just to facilitate the downloading, which means when I first initialize or instantiate the class into an object, this function is automatically called, and then the data will be automatically downloaded, right? This is what happens when I initialize the object. And let me just illustrate here. So I call this class and then pass in the parameters for figure pair, start dates, and end dates. And you see this message below, so which means it started to download, and the downloaded data is stored as part of the attributes in this object, right? So that's part of attribute, which is exactly in the scope attribute here. Right, so next, let's look at the default function. Here we have the entry and exit thresholds along with the window size, which are labeled as optional way to try out. So here, I first copy the stock data because this will be the data frame I'll be playing around with. And then I extract the usual Y variable and X variable as the constant of ones, which is a bell tree, by the ordinary squares regression, which fits the linear line. Then for the function fits to determine the model. Once you have the model, then obtain the spread, which is the difference between the targets and the predicted value, right? So this is the, of course, there are many other ways to calculate what is the spread, and there's no correct answer for what is the spread. This is just based on our simple definition here. This spread, and I'm using the rolling mean and standard deviation of this window size to be my benchmark to compare with, right? So there's mean and standard deviation. Now we get a z-score. So I'm just repeating the same procedure we did earlier. Next, we get the first index with the valid values, right? It's not NA because we use the window size here. So first, valid index, and then extract the z-scores, initialize two series for our positions, right? So one and two positions, and then apply this for loop here. So this for loop is something we explained last time. This chunk of code explains the generation of the trading signals in terms of the positions in different stocks, right? So I just skipped the codes here. You can refer to the previous video on how this works. So have these two stock positions and get the total returns. Then with these total returns, then I apply the annualization. So this code completes annualization, right? So first convert it to 1 plus R, performs compounding to get the terminal return in the 1 plus R format. Bring it down to an annual basis. So this is to see how much of a skill do we need to apply, and then convert to the simple return format. This is annualized return. Similarly, we get the annualized volatility. In this case, it scales the variance scales linearly. So this is daily return, and I'm just going to raise the power of 252 trading days, and then square root because this is a volatility, right? So now if the volatility is 0 and I set to 100, which is a big number. Okay, so finally I calculate the Sharpe ratio and set it as the return of the function, the forward function. So a special thing about this neural network module is that when we call the class itself, when we call the object itself, it calls the underlying the forward function. Right? So let me illustrate. So here again we have the source data, let me say Google and Microsoft, and then here we have the entry and exit signals thresholds. So when we set the parameters and call this object, underlying the forward function is called. That's why it returns me a Sharpe ratio of 1.69, right? And then if I change the parameters, then I have a new Sharpe ratio. So now the problem is, what is the optimal set of parameters such as the Sharpe ratio is maximized, right? So that's something we're going to do with Bayesian optimization. So here we have, let's first generate some training data. So I have the device again. PyTorch is based on the PyTorch framework, so which means it can leverage a GPT acceleration utility, right? So I'm just drag the device to see the GPT level, and then data type. So this is a boundary for the two parameters. The first parameter, which corresponds to the entry thresholds, is allowed to vary between 1 and 3, right? So this is a range of sets, and again, this is this boundary for the exit signals. Yeah, these are two signals. And then I'm going to generate three random points with random training sets. So the process of generating the random initial locations is that I would randomly sample, right? Randomly sample from these two ranges. So first, for the X1, which corresponds to the entry signal, I first generate a random number, which is between 0 and 1. And this does nothing more than scale it, right? Translate it into this range 1 and 3, right? For the second parameter, because it's already between 0 and 1, so I do not need to scale it up. So I can concatenate them together. So this is our training set in terms of the locations. And for each location, I would use a for loop to calculate the corresponding Sharpe ratio. This is to get the corresponding Sharpe ratio and then append it to the list I have. So this is the list in terms of the observed Sharpe ratios for these few locations. Then I'm also tracking the current maximum Sharpe ratio, right, observed so far. So now I'm just generating 3 initial observations, and then we can observe the values. So we have 3 entries, right, for the different parameters, and we have 3 different Sharpe ratios. So this will be used to initialize the underlying models in Bayesian optimization. Right, so this completes this performs the initialization. In this function, I'm just passing the training data in terms of X and Y, right, using the single task Gaussian process, which is the model I use to approximate the underlying true function. and then calculate the exact marginal log likelihood. Again, the reason I use this is to help me optimize the GP model at hand, right? And I've commented out some codes here. Again, this allows us to add the noise into the observation itself. So this is just to retain the model and the likelihood itself. So we initialize it, and then we check the hyperparameters of the model. You see that we have 2, 0, 0, and 0 for different parameters. Right? So now I'm going to use the fixed PyTorch ML to optimize these hyperparameters, because the GP model itself can also be optimized to better fit the data at hand. Right, so I'm just going to optimize it, then check the hyperparameters again. So you see these are the parameters that are optimized. So now I can, so now my GP model, the Gaussian process model, is already optimized. Then I can use it to move it to the next component, which is the acquisition function. In this case, I'm using 4 different policies. So one policy corresponds to one acquisition function. So I have expected improvement, Q expected improvement, which is the parallel version. The upper confidence bound, and the Q knowledge gradient, which is a more advanced acquisition function that encourages more exploration. Right, so I'm just same thing, generating 3 data sets, 3 points, and then assign this to each policy. So I have created these different variables. Okay, so just change names, and then initialize the model, the same thing for each policy. And then again, initialize the acquisition function. So expect improvements, Q expect improvements. Each function, the parameters may not be the same. So their parameters are different, especially for the QKG. It asks for more parameters because it does the internally performs the Monte Carlo simulations, right, for what would happen in the future. Right, so this telling the model to say I want to perform 64 rounds of fantasized simulations. Right, so so next we form the bounds, the search bounds, by adding all the predefined bounds together in one variable. And then this is number of batch, because we are still performing proposing 1 point per iteration. So we just set to 1. This is for optimization, which is in this case we're using the multi-start optimization. So we just set to 10 to get 10 initial rounds of multi-starts. And then this is the raw parameters again used for optimization in the initial phase. So here I'm defining this function, so that's when we take in the acquisition function of our choice. That way, use the optimized acquisition function to get proposals. So here we propose candidates in terms of location, and then the value of the acquisition function. Right. So this completes performing the maximization of the acquisition function. So after we get a proposal, we get the location, right? We calculate, and then obtain the corresponding sharp in the UI. Then converts format, then we return it. So this is the core function we use to get the next sample, the next proposal. All right. So you can see that if we pass in QPG, then it propose me this new parameters to try out. The corresponding sharp ratio is 2.2, right? So as a benchmark, we also maintain a policy based on purely random choice. So for each new edits, we just randomly sample, and then get the corresponding sharp ratio. So every time we random sample, and we're going to assess if our strategy based on Bayesian optimization outperforms the random sampling strategy. All right, so let's perform the sequential search. We're going to perform the sequential search for 20 rounds, right? And these are our parameters. Let me just jump to the core loop here. So we are looping for 20 iterations. For each iteration, we first fix the GP model, right? Optimize the Gaussian process, because we need to do it every time when there's a new data comes in, or you get a new, a better fitted GPU model. Then for each model, we for each round, we first initialize the corresponding acquisition functions, the same codes as before, and then get proposals for each policy. Right? So there's proposal for EI, proposal for QEI, etc. And then we're going to append the proposal to the existing training data set. Right? This first will select them into the historical data set, and then after the progress in terms of the cumulative maximum, right? So cumulative maximum is, for example, here we have the existing maximum, and then have the new proposal to see which one is higher. And then we keep the higher candidates appended to the best observed variables, observations, right? So this is just to maintain a list of the running maxes, cumulative maxes. Right, and then finally we introduce the model again, just so that they are good to use in the next round of iteration. Okay, so that's a mouthful for explanation, but let's look at the results. So the result shows that as iteration proceeds, the Sharpe ratio identified is like this. So we have the orange line, which is the from the EI, it's EI, or okay, so it's from UCB. UCB obtains the highest Sharpe ratio in the least number of iterations. That's good. And similarly for this with QEI and EI also catch up later. The QPG is exploring more. So in this case, it's not getting a higher value, but still all of them are better than the random strategy, right? So this shows that the Bayesian optimization is much more efficient and effective in locating the global maximum Sharpe ratio. All right. So this is just one iteration. The course next is just to repeat the same experiment for multiple times. And the reason is because usually we want to see not only the results, but also the stability of the results. So I'm repeating the same experiment by 4 times. And then the codes are exactly the same, skipping it, and then plots out the mean and then the also standard deviation. So here is the result, but it's a bit overlapping. So I also extracted the last value, right? So as the last iteration, what is the achievement for different policies, right? And just extracting the mean and the standard deviation for each policy as the last one. And we see that the UCB is the highest, right? It's expected. And then all of them are higher than the random strategy. And also the orange is smaller than the random strategy. So yes, it basically shows that the approach itself is stable and it is effective and efficient in locating the higher performing, better performing parameters for the health student strategy. All right, so that's it for this video, and thanks for watching.